Yeah, today we're doing section 4.7, scientific notation. And as the name implies, scientific, it's a notation of mathematics used a lot in sciences for large, very large numbers and very small numbers. When we're talking about the size of an atom, no, not like Adam and Eve, but an atom, like an oxygen atom, things like that. They're very, very small. Or you could say that there's billions and trillions and upon billions and trillions of them, and that number is a very large number. So whenever we need to deal with very large and very small numbers, we use scientific notation. If you were to take a chemistry course, scientific notation would be used extensively. So it's a good thing that you learn it here how to use it. Section 4.7, we're going to start off going over a couple examples. Now, there's some reading, of course, in the book that I expect you to do. I'm not going to do any of the reading. I'm just going to go straight to example 1. This is on page 3. And let's just see what it says. It says for us to rewrite each expression, such as 900, as a product of a number, a whole number, and a power of 10. For example, 900 is 9 times 100. Now this is the product of a number, 9, and a power of 10, 100, but we can also express this power of 10 in exponential notation. 100 is like 10 squared. And so this could also be rewritten as 9 times 10 squared. What makes this so simple is that the power of 10, 2, indicates the number of zeros in the number that we have here. So if there are 2 zeros, it'll be 10 squared. Likewise, with a number such as 5,000, we can express that as 5 times 10 to the third power. That's right. 3 zeros, third power. Let's see, part C, 800,000. Just a matter of 8 times 10 to, well, counting up how many zeros we have. 1, 2, 3, 4, 5. So that's 10 to the 5th. And you get the idea. I don't need to do part D. You've got the idea already. Similarly, on page 4.7-4, example 2, we have a small number, actually 2 small numbers. And these can also be represented in the same way, except small numbers are represented with negative exponents, negative powers of 10. So when I see 0.04, number of ways I can think of this. But one of the best to start with is that this is 4 hundredths. 4 hundredths. Or 4 over 100. Now I'm going to do something a little bit backwards than what you're used to seeing. Think of that 4 over 100 as 4 over the 10 squared. And where it's going to get a little bit backwards, this comes from section 4.6. Remember that if we have a negative exponent, I don't know why I choose 4, but 4 to the negative 2 is 1 over 4 squared. Well, if we started with 1 over 4 squared, I could rewrite it as 4, the base, to the negative power. Well, the same thing down here. This 10 squared could be written up above, or multiplied times the 4, 10 to the negative 2. 10 to the negative 2. And recall that the negative exponent has meaning, and its meaning is reciprocal, and that negative exponents tend to and usually represent small numbers. Well, that's a small number. It's a decimal number. We'll consider it a small number. These are very large numbers up here. These are relatively small numbers here. So really, let me rewrite this. 0.04 can be 4, or 4 times 10 to the negative 2. So we recognize that it's a small number because it's a decimal number, which indicates that it's a negative exponent on 10. Also, how many decimal places are there? That's right, there are 2 decimal places. So that's why it's to the negative 2 power. Let's see how that works on part B, which is 0.00009. How many decimal places are there in all? After the decimal point, there's 1, 2, 3, 4, 5, counting the 9. So there are 4 zeros and 1 extra place. So this is 9 times 10 to a power. Is that power going to be positive or negative? That's right. That's right. It's negative because it's a small number. And it's a positive number, but the exponent for 10 is negative. Small numbers, negative exponents. Look at these large numbers over here. Positive exponent, positive exponents. Small numbers, negative exponents. So that'll be times 10 to the negative something. Again, that value is the number of places after the decimal point. Here we had 2 places. Only 1 0, but 2 decimal places. So it's negative 2. Here we have 4 zeros. A 5th decimal place, though, so it'll be negative 5 up here. 9 times 10 to the negative 5. Okay? Very good. So the examples in the book and the exercises here are setting you up for what we're about to see next. Setting you up for really understanding scientific notation. So a lot of the stuff I was doing here is simply a matter of preparation for scientific notation. So let's go ahead to what scientific notation actually is. Scientific notation is a product. Now, product means, that's right, multiply or multiplication of 2 factors. And factors means multiplication too, so it's almost redundant, but it's good to have it spelled out that way. Scientific notation is a product of 2 factors. Here's the first factor. A numerical coefficient such as 3.6, 1.09, or 9.45. These are possible coefficients. And of course there are many, many others. So that's one of the factors, is this numerical coefficient. And the other is a power of 10, such as maybe 10 to the 5th or 10 to the negative 3. In other words, this power of 10 could have a positive exponent, and it would if it's a large number, or a negative exponent, and it will if it's a small number. So with that in mind, let's talk more about this numerical coefficient. The numerical coefficient is going to have a single digit followed by a decimal point, usually, not always, but usually followed by whatever digits there are. And this right here is a single digit, not 0. We're not going to count 0 in this case as the lead single digit. It's a whole number. That's the whole number part. But it's just a single digit, and it can't be 0. So when we see the numbers that I have up here, like the 3.6, there's the single digit, followed by a decimal point and a number. 1.09, single digit, 1, not 0, and then followed by 2 decimal places, a decimal point and 2 decimal places. And the same thing is true for 9.45. What about this? What about 0.35? Is that the numerical kind of numerical coefficient that we want for scientific notation? Well, it can be a numerical coefficient, but it turns out that it's not in proper form, and that's because this here is 0, which means we need to adjust this somehow if we want it to be a part, or if we want it to be the numerical coefficient in scientific notation. We'll have to adjust this whole coefficient here probably to be 3.5, because then we'd have it where the decimal point is right there, and we have a lead digit, a whole number digit, that's just a single digit. So when we look at example 3 now, example 3, and that's on page 5, so page 4.7-5, you can look there. It gives us a number, and it asks us, could it be the numerical coefficient when it's in proper scientific notation? You know, even this one right here can be a coefficient, but it's not in proper scientific notation if we leave it like this. So we've got to find a way to adjust it. But in part A, we have 9.75. Is that a proper coefficient for scientific notation? Well, just look right here. Whole number is a single digit. So the answer, without any more work, is yes, that's legitimate. That's allowed. Part B is 15.4. Look at the whole number, you know, the number that comes before the decimal point. 2 digits, it's fine in general as a regular coefficient, but it's not a proper coefficient, not one that puts it in proper scientific notation. So we'd have to do some adjustment here. So the answer to the question, though, is no, it's not in proper scientific notation if that's the coefficient. Let's see what part C says. Oh, just has 4. Well, yes, this is actually okay. I should have put here that yes, this is okay as well. We don't have to have a decimal point after it. It can be just a whole number like that. Sometimes, though, just for emphasis, we might make it 4.0. But in either case, 4 is a legitimate, proper scientific notation coefficient. And here the 0.56, as it is, the answer is no. Very good. And that's because? Yes, that's because the 0 here, it can't be 0 for that single digit to be proper scientific notation. Okay? Very good. So, our next challenge is to write large numbers in scientific notation. Take, for example, well, we'll look at example 4. This is on page 4.7-6. Example 4. Before I do, I'm going to write 4A here, and then I'm going to do a kind of a preparation exercise. 960,000. We would consider this to be a large number, and we'll be able to simplify the way it looks using scientific notation. I shouldn't say it that way. We'll be able to write it in scientific notation. They don't always look all that simple when they're written that way, but to a scientist, that would be the kind of numbers that they would want to work with. But before we actually do that problem, let me remind you of a problem similar to this, 900,000. In this one, we said that that was 9 times 10 to a power, and we counted up the number of zeros. And we see 1, 2, 3, 4, 5 zeros, and it's a large number, so that'll be 10 to the positive 5, 9 times 10 to the 5th. Now, what do you think about making this, and I'm just going to put a question mark here for now, as 96 times 10 to the, let's count up the number of zeros. 1, 2, 3, 4. 4 zeros. What do you think about making it 96 times 10 to the 4th? Is it true that it's equal to 96 times 10 to the 4th? Sure it is. That's a true statement. But is it in proper scientific notation? That's the main question. The answer is right. It's no, it's not, and because? Yep, the coefficient has 2 digits in the whole number. Now, we said we don't have to have a decimal point, but we certainly can't have 2 digits in the whole number. So we actually want the decimal point to be right there. The thing is, this 960,000 is somewhat more than 900,000. Now, 900,000 itself was 9 times 10 to the 5th. Counted up 5 zeros. Do you agree that I could write this as 9, like 9.0 times 10 to the 5th? Do you agree with that? You know, 9 is just 9.0. 9, we could put as many zeros as we want after it, actually, but you know, that's the same number, right? 9 and 9.0. So, if we thought of it this way, that would be like putting a decimal point right here. Oh, yeah, just after the 9. Just like down here I want to put it right after the 9. Here I put it right after the 9. But still, it's 10 to the 5th power. In other words, we count up the places from the end. If we did have a decimal point, how many places would we have beyond the 9? That's what would give us, you know, that we have in our large number here. That's what tells us the exponent. So, again, how many places after the 9? It's going to be 9.6 that we want here, not 96. 9.6 times 10 to the something. And it's a large number, so it's going to be a positive exponent. But what do we want? How many places are there after the 9? There's 1, 2, yes, I counted the 6. That's right. 1, 2, 3, 4, 5. There are 5 places after the 9. So the 9.6 times 10 to the 5th is the way we'd represent this in scientific notation. This is for a large number. Let's do part B. Part B says 745 million. 1, 2, 3, 4, 5, 6 zeros in all. And yet, proper scientific notation says it has to be 7 point something. Well, 7.45 times 10 to a power. Now, what is that power? Is it going to be just the 6 zeros that we see here? If we consider just the 6 zeros, then the coefficient should be 745. 745. But we don't want it to be 745. It's 7.45. And that means that we wanted our decimal point to be right here. And that means that we have a total of not only just these 6 zeros, but 2 more places beyond the 7. Or if we started from here, we'd have 1, 2, 3, 4, 5, 6, 7, 8. 8 places, excuse me, beyond the 7. So that's why it's going to be 10 to the 8th power. Should that be 10 to the negative 8? I don't think so. How come? Exactly. Yeah, that's right. This is a large number. This right here, this number right here is 745 million. That's a very large number. And because it's such a large number, it's going to be a positive exponent. As long as it's a large number, it's a positive exponent on the 10. If it were a small number, then we'd have negative exponents. In fact, our next example is going to be just that. Example 5 on page 8. Let's take a look at that. And that's on page 8, page 4.7-8. Part A, in example 5, says we have 0.00096. Now to put this in proper scientific notation, where is the decimal going to go for the coefficient? Did you say between the 9 and the 6? Well, you were thinking it. I know you probably didn't say it out loud to anybody, but yeah, between the 9 and the 6. So that's going to be equal to 9.6 times 10 to the something. Now, before I even do any counting, notice this. This number is a small number. It's a decimal number. It's a very small number, less than 1. So that means, what about our exponent? Exactly. It's going to be negative. But how much negative? Well, think about where I want the decimal point. And I want that after the 9, actually between the 9 and the 6. And here it is right here. So we can actually think of moving the decimal point, and however many spaces we move it, that'll be the exponent up here. So we might think of it this way. Let's see, if we moved it, it would be 1 place, 2 places, 3 places, 4. So 9.6 times 10 to the negative 4. would be the proper scientific notation for that number. Let me write it in black. So we have 9.6 times 10 to the negative 4. So what's the steps so far that we've seen for these numbers up here and down here? Identify where the decimal point would need to be for the proper coefficient. Here, 9.6. Here, 7.45. Here, oh, look, again, 9.6. Identify whether it's a large number or a small number, meaning very small, decimal number. Large numbers have positive exponents on 10. Small numbers, very small numbers, have negative exponents for 10. So, and then we simply need to identify, how far over do we need to move a decimal, or just, how many places do we need to count to get there? And that's, that's the procedure, that's the approach, the strategy for deciding how to write these numbers. What's the next example here? Wow. Excuse me, I gotta count up some zeros here. 1, 2, 3, 4, 5, 6. That's kind of hard to count. Just a moment. 1, 2, 3, 4, 5, 6, 7, 8, and then 7, 4, 5. So let me see. 0 point. 1, 2, 3, 4, 5, 6, 7, 8, 7, 4, 5. By the way, notice that as I counted this out, I was not counting the 0 in front. I'm only concerned about or interested in the zeros that are after the decimal point, what comes after the decimal point. And here we want it to be, just like before, in the letter B up above, 7.45. That's going to be the coefficient. 7.45 times 10 to what kind of power? Yep, that's right, a negative power, because, yeah, that's right, it's a small number. So it's a negative power. I could put that on before I put anything else even, before I figure out what the number is. Now, let's consider what the number is. Notice, first of all, I had 8 zeros here, and that 8 zeros take us right up to 7, but we want to go one place beyond it. The 8 zeros, boom, 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 and then one extra place beyond it to 9 zeros, or 9 places in all. And so that's why this is going to be 10 to the negative 9th power. 7.45 times 10 to the negative 9. Okay? Making sense so far? I hope so. I hope so. Let me erase all of this. And if you need to go back and review it, you certainly can, and move the little slider bar to the left and review that as you need to. I'm going to clear it all for now. I'm going to go on to page 4.7-9. Example 6. And here we're asked to expand a number. And part A is a positive exponent and part B is a negative exponent. We're going to expand it so it's no longer in scientific notation, and it's in its real number form. So we start with part A, which is 4.6 times 10 to the 4th power. 4th power. Okay. Now, and I'll kind of proceed this a little bit, if it had been just 4 times 10 to the 4th, then we would say, that's 4 and 4 zeros. 1, 2, 3, 4, which makes it 40,000. What would it be if it were 4.0 times 10 to the 4th? Would it be the same thing, 40,000? Let me fix that a little bit. Well, the 4 and the 4, they're the same coefficient. I just put a 0.0 after it's the same value though. So yeah, it should still be 40,000. Well, let's take a look at how it is we might get to have that be 40,000. One thing that we can always do with decimal numbers is place as many zeros on the end as we wish. So I can put tons of zeros here, as many as I need. I think that's more than enough, actually. And the effect of working with this large number, first of all, we know that our answer is going to be large, and 40,000 is a pretty large number. But the effect of getting it to be 40,000 means that we have kind of moved the decimal point. Here it is 4.0. We've moved it in such a way that it ends up being way on the end. Normally we wouldn't even write it in. I'll just put it in here, say there's the decimal point in red, or there's the decimal point. We don't need to represent it with a large number like that. But the idea is, in effect, we're going to move this 1, 2, 3, 4 places. Moving it 4 places creates our large number. And I'm going to write that large number without any commas, 4, and then 1, 2, 3, 4 zeros, and I'm going to count back 3 to get 40,000. Let me do the same thing for 4.6 now. I mean the actual example at hand. 4.6. Let me place a bunch of zeros after it, and it doesn't change the value, but I want to now move that decimal point 4 places to create a large number. So I'm going to go 1, 2, 3, 4 places. I'm going to get rid of these. I don't need those. And I'm going to rewrite the number before I even write a comma. 46000. And now I'll count back 3 places to put a comma right there. 46,000. It's a large number, and that's what we have. 46,000. Part B, 8.07 times 10 to the negative 5. Negative exponent means what? Yeah, very small number. That means that our decimal is actually going to be over here somewhere, before the 8. Be over here somewhere. And we can do the same process of moving the decimal point that many places, but here we're going to have to move it in such a way that we create a small number. Well, just like we can place any number of zeros after decimal point, we can also place as many zeros in front of a whole number, and it's not going to change its value. But we do this to help us decide what our expanded number is going to be. We have to move it 5 places, and we have to do it in a way that it creates a small number because of the negative. So that means I'm going to have to move it back this way 5 places. So let's see what we get here when we move it back 5 places. 1, 2, 3, 4, 5. Okay? Now, what we get out of this is a decimal point right there, and then 0, 0, 0, 0, 8, 0, 7. And we no longer have a decimal point within that. And usually, we'll represent it as 0.0000, excuse me, I can't, that was way too many. 0.0000807. That's the expanded form. It's no longer in scientific notation. Is it okay that we have a 0 here? No, wait a minute. This is okay this time to put that 0 here because this is not a coefficient of a number like we would have up here. This is no longer in scientific notation. Having the whole number first is when we put it in scientific notation. In scientific notation, this has to be a single digit, and it can't be 0. But this is expanded form, so yes, it's okay to have the 0 here in expanded form. Okay? All right.